Have you ever wondered, in the gentle stillness of the night, what the universe is doing as you lie there, breathing slowly in the darkness? Because even now, as you settle into rest, an immense cosmic story continues to unfold around you. At this very moment, space itself is stretching at around 700,000 miles an hour, and that stretching is sweeping distant galaxies away from us, faster than light could cross the same distance. With every passing second, the universe becomes larger in a way that defies ordinary intuition, and yet it expands into nothing at all. It is one of those cosmic facts that unsettles the mind because it asks you to let go of how you think space should behave. Consider something even stranger. In an expanding universe, every location can describe itself as the center of the whole story. And then there is the invisible ingredient, the one that seems to account for roughly 70% of what exists driving the expansion onward. Follow the mathematics far enough, and it even hints at a final moment, a last breath of the cosmos. If you are willing to go there, then let us begin. Space itself moves. Here is the truth that makes your brain hesitate. The vast emptiness between galaxies is not static. It stretches like an unseen elastic fabric. The distance from here to the nearest star increases imperceptibly, second by second. Space expands, and everything embedded within it is carried along. It is tempting to imagine that empty space is simply nothing. It is not. Space is the arena in which physics happens, and it has properties. It curves near mass. It can ripple with gravitational waves. And most astonishingly, it can grow. When you inflate a balloon, the rubber expands into the room around it. The room provides the extra space the balloon seems to occupy. But the universe contains all the room there is. It expands without expanding into anything else. Imagine for a moment that you live on the surface of a balloon and you have no capacity to see above or below that surface. Your entire reality is confined to that curved skin. As the balloon is inflated, every point on the surface recedes from every other point. From within that two-dimensional world, it would feel as though space itself is growing. There is no outside for that surface to expand into, because outside is not part of the world you can describe. Now add one more dimension. We live in three-dimensional space, and in the same way it can expand. The difference is that we do not perceive any dimension beyond the three we inhabit. And yet space can still increase within itself, creating more space as it grows. Physicists call this intrinsic expansion. The universe is not pushing outward into some surrounding void. Space itself becomes larger. The very scale with which you measure reality stretches, and it does so everywhere at once. Between the atoms in your body, the effect is utterly overwhelmed by the electromagnetic forces that bind matter together. Between stars inside a galaxy, gravity wins and keeps systems intact. But across the enormous gulfs between clusters of galaxies separated by millions of light years, there is nothing strong enough to halt the steady, relentless growth of space. The numbers are startling. Each second, a region of space 1 million light years across increases by roughly 22 meters. Over cosmic distances, that translates into galaxies millions of light years away, being carried from us at hundreds of thousands of miles an hour. Not because they are flying through space like projectiles, but because the space between us and them is stretching and they ride that expansion. In 1929, Edwin Hubble uncovered this expansion observationally. He found that galaxies beyond our local group are moving away from us, and the farther away a galaxy is, the faster it recedes. That simple pattern can create the illusion that we sit at the center of everything. We do not. Any galaxy anywhere would see the same overall behavior. Expansion does not privilege a special location. This expansion began about 13.8 billion years ago, when space and time themselves came into being. Since then, the universe has grown by a factor so vast that even describing it becomes a challenge. Something that was once smaller than an atom corresponds in our modern universe to scales that reach across billions of light years. And Hubble's work revealed something that feels almost confrontational. Some galaxies appear to recede from us at speeds that outstrip what light could cover over the same stretch of time. In 1929, looking through what was then the largest telescope on Earth, Hubble did not find a quiet, eternal cosmos. He found a universe in motion, with galaxies slipping away from the Milky Way, as though the whole fabric of space were carrying them outward. This upended the prevailing picture of the day. Einstein, for his part, had expected a universe that was static and unchanging. When his own equations pointed naturally toward expansion, he introduced an extra mathematical term to hold the universe still. Later, he would refer to that decision as his greatest mistake. Hubble measured the speeds of galaxies using a kind of cosmic fingerprint. Each chemical element emits light at specific colors and wavelengths when it is excited. Hydrogen produces characteristic red light at a precise wavelength. Helium has its own distinctive signature at exact frequencies. These patterns are reliable, like an identity card written into the spectrum. But Hubble found something that seemed impossible at first glance. When Edwin Hubble began to examine the spectra of distant galaxies, the familiar fingerprints of hydrogen and helium were there, but shifted, drawn out toward the red end of the spectrum, and the pattern was unmistakable. The more distant the galaxy, the deeper the shift. Redshift wasn't just a curious detail in the light, it was a message. Those galaxies were receding from us at extraordinary speed, and when he put numbers to it, the universe started to speak in a kind of simple arithmetic. A galaxy 2 million light years away was moving away at roughly 45 meters per second. At 4 million light years, it was about 90. Twice the distance, twice the speed. Over and over again, wherever he looked, that relationship held. That is what we now call Hubble's law. The recession speed is proportional to distance, with the constant of proportionality being the Hubble constant, which we measure today at around 70 kilometers per second per megaparsec. If you translate that into something a bit more intuitive, it means that for every 3.75 million light years you go out, galaxies are receding about 43 meters per second faster. The consequences were profound, because if everything is moving away from everything else, then in the past everything must have been closer together. Wind the cosmic film backwards far enough, and mathematically all the matter in the universe is driven into an arbitrarily small, immensely dense state. That line of reasoning leads straight to the Big Bang. Hubble's discovery turned the universe from something eternal and unchanging into something with a history, with an age. Space itself has been expanding for about 13.8 billion years, emerging from conditions so hot and so dense that our everyday intuition simply fails. And before that, there isn't a sensible meaning to before in the way we normally use the word, because space and time are part of the story that begins with that expansion. It also helps resolve a question that once troubled astronomers. Why is the night sky dark? In an infinite, eternal, static universe, every line of sight should eventually end on a star, and the sky ought to blaze. But it doesn't. Much of the universe is hidden from us simply because light from the most distant regions has not had enough time to arrive. And then there is something even more unsettling. At sufficiently large distances, galaxies recede so quickly that their recession speed exceeds the speed of light. Beyond a certain horizon, they vanish from our view, not because their light is dim, but because the space between us and them grows too fast for their light ever to reach us. Modern observations have reinforced this picture with remarkable accuracy. Instruments, including the James Webb Space Telescope, have refined distance measurements to extremely high precision, and the evidence continues to point in the same direction. The universe is expanding, and it does so relentlessly. But that leads to a question that seems almost paradoxical at first. If everything is expanding away from everything else, why does every observer feel as though they are at the center of it? The simplest way to see it is with a balloon. Imagine a deflated balloon and mark dots across its surface, each dot a galaxy. Now inflate it slowly. As the rubber stretches, every dot moves away from every other dot. Focus on any one dot, and the effect looks the same. Choose the dot you call the Milky Way, and you'll see all the others receding in every direction, with the more distant ones separating faster. Shift your attention to a different dot, say Andromeda, and suddenly Andromeda seems to be the center, with the Milky Way moving away, and the more distant dots fleeing faster still. That is the essential point. The expansion looks the same from every location. There is no privileged center, no special address in the cosmos. And the balloon shows something else that matters. The dots are not crawling across the rubber, they are carried along as the rubber itself stretches. In the same way, galaxies are not generally flying through space as much as space itself is growing between them. Locally, galaxies can be nearly at rest relative to their surroundings, while the fabric of space expands on the largest scales. That is why apparent recession speeds can exceed the speed of light without contradicting Einstein. The cosmic speed limit applies to motion through space. It does not constrain the rate at which space itself can expand. When space expands quickly enough, it can sweep distant galaxies away from us faster than light itself. Imagine a galaxy around 15 billion light years from here. The space between us and that galaxy is stretching so rapidly that the distance grows at about 1.5 times the speed of light. The galaxy is not racing through space at extraordinary speed. It is almost at rest in its local region. The astonishing motion comes from the expansion of space between us. The familiar balloon analogy helps, but only to a point. A real balloon expands into the room around it. The universe expands into nothing at all. A balloon has an inside and an outside. The universe does not. It contains everything that exists. So we must picture a balloon that is only surface, where inside and outside simply have no meaning. Mathematicians describe this as intrinsic expansion rather than extrinsic. The surface grows from within itself without needing any surrounding space. Our three-dimensional universe behaves in exactly this way. Space grows larger without requiring a fourth spatial direction to expand into, and on the largest scales, this growth affects everything evenly. From any galaxy, the view of cosmic expansion is the same. Any intelligent civilization that studies the heavens will uncover the same Hubble law. They will see galaxies streaming away in every direction. Yet this calm and orderly expansion began in an instant of unimaginable violence. Space and time themselves came into being from absolute nothingness. 13.8 billion years ago, the entire universe was smaller than the full stop at the end of this sentence. All the matter that would later form hundreds of billions of galaxies was compressed into a region far smaller than a proton. Temperatures soared to 100 million trillion degrees, a realm where our current physics can no longer guide us. Then expansion began. The earliest moment is beyond intuition. There was no space for expansion to occur within, and no time in which events could unfold. Before and after had no meaning. Space and time emerged together, carrying with them all the matter and energy the universe would ever possess. We call this event the Big Bang, though the name invites the wrong picture. It suggests an explosion blasting material into empty space. That is not what happened. Space itself began to expand, taking everything with it. There was no explosion because there was nowhere for one to take place. Within the first second, the universe experienced the most extreme transformation in its entire history. During a brief phase known as inflation, space expanded at a rate beyond anything we can measure today. The universe grew by a factor of 1 followed by 26 zeros in a fraction of the time it takes light to cross a proton. Regions once smaller than atomic nuclei were stretched to sizes comparable to basketballs. This episode of inflation answers some of the deepest puzzles in cosmology. The universe looks almost perfectly uniform in every direction. Regions that were never close enough to exchange information share the same temperature and structure. Inflation explains this by magnifying tiny uniform patches of space to cosmic scales. When inflation ended, the universe was still extraordinarily hot and dense. For the next 380,000 years, space itself glowed like the interior of a star. Free electrons scattered light, constantly making the universe opaque. Seeing through it was as impossible as seeing through the surface of the sundae. Then came a pivotal moment known as recombination, when expansion cooled the universe enough for electrons to bind with atomic nuclei for the first time. At that instant, light was set free, space became transparent, and the cosmic fog lifted forever. That ancient light still travels through the universe today. We observe it as the cosmic microwave background radiation. Wherever we look, this faint afterglow fills the sky. It is the oldest light that exists. It is a baby photograph of the universe taken when it was only 380,000 years old. Its temperature matches theoretical predictions with remarkable precision. Subtle variations within it reveal where the first galaxies would eventually form. The pattern confirms that space has been expanding for nearly 14 billion years. Modern measurements show that the cosmos has stretched itself by a factor of roughly 1,100 since the moment the cosmic microwave background was released. A region once only a mile across has been drawn out to more than 1,000 miles, carried along by the quiet but relentless growth of space. That expansion persists today, and remarkably, it accelerates. The idea born from the Big Bang carries an extraordinary implication. If everything emerged from something unimaginably small, then by rewinding this cosmic film, we can infer the moment of its beginning. Independent lines of evidence converge on an age of about 13.8 billion years, with only a slight margin of uncertainty. Yet it is the behavior of galaxies in this expanding arena that reveals something even more astonishing. Galaxies drift apart not because they are shooting through space, but because space itself stretches between them. Imagine a bowl of warm dough rising gently in the oven, raisins scattered throughout. As the dough swells to twice its size, the raisins are carried along, each one separating from the others without ever moving through the dough. A raisin that began 2 inches away from its neighbor becomes 4 inches distant. In this simple kitchen image lies a faithful illustration of cosmic expansion. The galaxies are the raisins. The unseen geometry of space is the dough. As it grows, it bears the galaxies with it, increasing their separation without the galaxies actually traveling. This picture resolves several long-standing puzzles. Galaxies do not race through space at extreme speeds. They meander slowly within their local neighborhoods, while the space around them expands. And importantly, the expansion acts uniformly. Every patch of space grows at the same proportional rate, just as every part of the dough rises together. Here the numbers become almost surreal. Space expands at roughly 70 kilometers per second for every megaparsec of distance. Put more simply, for every 3 to 4 million light years, the fabric of space increases by around 43 meters each second. Double the distance and the rate doubles. A galaxy 100 million light years away recedes at about 1,300 miles per second. At 1 billion light years, the recession climbs to 13,000 miles per second. At 10 billion light years, it reaches 130,000 miles per second. The most remote galaxies we can observe withdraw at nearly the speed of light. The raisin bread picture shows why. Measure the separation of 2 raisins spanning the full length of the loaf. As the dough doubles in size, they end up twice as far apart. From one raisin's vantage point, the other seems to have raced away. The same phenomenon plays out across cosmic distances. Each tiny region of space expands at a gentle pace, but accumulated over billions of light years, the retreat becomes immense. The galaxies themselves hardly budge. Almost all their apparent motion arises from the expansion of space between us and them. This is why galaxies can seem to move faster than light without infringing the laws of physics. Einstein's limit applies to motion through space, not to the growth of space itself. If space expands quickly enough, it can draw objects apart at velocities that eclipse the speed of light. There is, however, one subtle flaw in the bakery metaphor. Dough expands into the empty oven around it. The universe has no outside into which it grows. Space generates more space, as it expands like some conjuring dough that produces its own oven as it rises. Astronomers witness this growth directly by studying how light changes on its journey across the expanding cosmos. Some galaxies retreat faster than light can traverse the void, yet Einstein's rule remains untouched. 14 billion light years away, a galaxy can recede at nearly 200,000 miles per second, outstripping light by about 14,000 miles per second. It sounds like a violation, but only until we recall what Einstein actually forbade. No object can accelerate through space past the speed of light. Nothing with mass can race at 670 million miles per hour relative to its immediate surroundings. That edict remains unbreakable, but Einstein placed no restriction on the rate at which space itself might grow. To picture this, think of two ants strolling slowly across the surface of an inflating balloon. Their own motion is gentle, almost negligible. Yet as the balloon expands, the separation between them increases far faster than either ant can walk. In precisely the same way, galaxies move only modestly within their local domains, while space inflates around them, carrying them apart at effective speeds that can exceed the cosmic speed limit. They never violate Einstein's rule, because they hardly move through space at all. This leads to a profound boundary in the observable universe. Any galaxy receding faster than light will never be seen. Its light begins the journey toward us at 186,000 miles per second, but the space in between grows more quickly, pulling the galaxy away faster than its photons can close the gap. The light gains ground at first, but eventually the expansion overtakes it. Mathematics reveals the threshold. Beyond roughly 14 billion light-years, galaxies recede faster than light itself. This distance is known as the Hubble horizon. Anything beyond lies forever out of reach. Those galaxies may exist in the vast darkness, but their light will never arrive and no signal we send will ever find them. Even stranger still is the quiet inevitability that the galaxies we see today will one day drift beyond a boundary that marks the limit of what can ever be observed. As the expansion of the universe accelerates, one galaxy after another will slip across this cosmic horizon, vanishing from view. To those who live in the far future, the sky will appear increasingly barren as the great archipelago of galaxies gradually recedes into darkness. And yet, while the most distant systems flee faster than light can bridge the growing gulf, the light that does reach us from nearer realms tells a subtler story. Imagine photons released by a galaxy 8 billion light years away. When those photons began their long journey, the galaxy itself stood far closer than it does today. Over those billions of years, space has stretched relentlessly, carrying the galaxy outward, while simultaneously elongating the very waves of light streaming toward us. Their wavelengths grow longer, their energy diminishes, and the colors they once possessed slip down the spectrum. Blue fades to green, green to red, red to the cold whisper of the infrared. The farther the galaxy, the greater the stretching, giving the most remote objects an extraordinary redness. This is cosmological redshift, not caused by motion through space, but by the steady expansion of space itself as the light travels across it. The degree of this reddening tells us precisely how much the universe has expanded during the light's passage. In extreme cases, ultraviolet light leaves its home galaxy only to reach us transformed into infrared radiation. This simple act of stretching is among the clearest demonstrations that space is still expanding. Yet this grand expansion imposes a profound limitation. There is a frontier beyond which nothing can ever send word to us. Light arriving from the most distant regions began its journey 46 billion years ago, even though the universe itself is only 13.8 billion years old. This seeming contradiction arises because space has been expanding beneath the feet of those photons for the entirety of their trip. When we gaze across the depths of the cosmos, we see galaxies as they were billions of years in the past, frozen in the light that has only just arrived. The most ancient signals we can detect were released when the universe was a mere 3,800,000 years old, and they have been travelling for 13.8 billion years to reach Earth. One might expect these objects to lie 13.8 billion light years away, but they do not. The expansion of space has carried them outward so effectively that they now reside roughly 46 billion light-years from us. This defines the observable universe, a vast sphere centered on Earth with a radius of 46 billion light-years. Everything that falls within this sphere can, in principle, send its light to us. Everything outside it remains forever hidden. No matter how advanced our instruments become, this horizon marks the absolute limit of what we can know through observation. Whatever lies beyond it, whether galaxies of unimaginable scale, unfamiliar physics, or perhaps even domains with entirely different properties, remains sealed behind a veil drawn by the expansion of space. This horizon also shapes what we can infer about the overall architecture of the cosmos. If the universe extends beyond what we can see, its full size and shape are unknowable to us. It might be infinite, or it might curve back upon itself like the surface of a sphere. Such truths are held forever in regions we will never access. More unsettling still is that the realm of galaxies visible to us is gradually shrinking in number. As the expansion accelerates, galaxies near the edge of observability recede ever faster. Eventually they cross a point at which space pushes them away more quickly than light can compensate. Their final photons leave them and fail to reach us, and those galaxies fade from our universe forever. Today we estimate that roughly 2 trillion galaxies populate our observable domain, each a sprawling collection of hundreds of billions of stars. Together they outnumber Earth's grains of sand by millions to one, and yet they represent only a sliver of what might exist beyond the horizon. The horizon also bounds our view of the past. The oldest light we can detect is the cosmic microwave background, released when the universe first became transparent, some 380000 years after the Big Bang. Before that era, the universe was opaque, preventing light from traveling freely. No telescope, however capable, can peer beyond this wall of radiation. To explore earlier epochs, we must rely on other tools, from gravitational waves to theoretical insight. The horizon itself expands at the speed of light, continually revealing new pockets of space. But because distant galaxies are swept away faster than this boundary grows, the number of galaxies within our observable universe slowly diminishes. In the remote future, those who look to the night sky will find themselves adrift in an ever emptier cosmic ocean. One by one, the great island universes scattered across the cosmos slip beyond a kind of cosmic horizon, carried away by the expansion of space, until only the small family of galaxies bound to us by gravity remains. In that distant era, the universe will appear sparse, containing only a few dozen galaxies rather than the trillions that populate it today. Yet within the light that still reaches us lies a subtle imprint stretched across unimaginable distances that whispers one of the universe's most profound truths. Photons are drawn out like strands of cosmic taffy as they traverse expanding space for billions of years. Picture a simple wave sketched onto the surface of an uninflated balloon. As the balloon expands, the wave elongates, its crest drifting further apart, its wavelength increasing. Light crossing a growing universe behaves in precisely the same way. The expansion of space itself tugs at each photon, lengthening its wavelength as it journeys across the cosmos. This stretching grants astronomers one of their most exquisite tools. When light leaves a remote galaxy, it carries the exact electromagnetic fingerprints of hydrogen, helium, and a host of other elements, locked into well-defined spectral lines that remain constant in their native state. Hydrogen emits a brilliant red at 656 nanometers. Helium shines yellow at 588 nanometers. But after billions of years of travel, something remarkable is revealed when that ancient light arrives. The familiar hydrogen line no longer sits at 656 nanometers, but at around 700, nudged toward the infrared. Helium shifts from yellow toward orange. Every elemental signature drifts to longer wavelengths. This is cosmological redshift, distinct from the Doppler effect we recognize when an ambulance speeds past. Doppler shift is born of motion through space. Cosmological redshift emerges because space itself stretches during the photon's voyage, pulling the wave apart like an elastic band. The degree of redshift tells us exactly how much the universe has grown since the moment the light was released. A redshift of 1 means the cosmos has doubled in size. A redshift of 2 means it has tripled. The most remote galaxies we can observe display redshifts greater than 10, signaling that the universe has expanded more than 11-fold during their light's transit. Such stretching transforms radiation in dramatic ways. Ultraviolet from distant systems arrives as visible light. Visible light drifts into the infrared. Infrared stretches into radio waves. Even X-rays from ancient quasars soften into visible wavelengths by the time they reach us. The James Webb Space Telescope is designed to observe in the infrared for this very reason, capturing the faint, stretched glow of the earliest galaxies. Redshift allows astronomers to determine distances with remarkable precision. The larger the redshift, the farther the galaxy sits in today's universe, because the expansion acts uniformly across space. A galaxy displaying twice the redshift of another is roughly twice as distant. But stretching the wavelength also saps energy from the light. Gamma rays from far-off supernovae may wash ashore on Earth as low-energy radio waves. As a result, the earliest galaxies appear astonishingly faint, mere pinpricks of brightness from across cosmic oceans, even though they blaze with the luminosity of more than 1 trillion suns. With redshifts measured for millions of galaxies, astronomers have constructed a vast three-dimensional map of cosmic structure. It reveals how matter gathered through the ages into galaxies and clusters, and shows that expansion dominates the voids between these great structures, while scarcely altering regions held together by gravity. The most dramatic redshift of all belongs to the cosmic microwave background, ancient light, dating from about 380000 years after the Big Bang. Its redshift of roughly 1100 tells us that the universe has expanded by this factor since that early moment. What began as radiant visible light from a searing plasma has been stretched into the faint microwaves that bathe the cosmos today. Yet, in recent years, exquisitely precise measurements of this cosmic redshift have uncovered a troubling discrepancy, a puzzle that hints at gaps in our understanding of the universe itself. A mysterious presence, stronger even than the familiar pull of gravity, is urging the cosmos apart with a steadily increasing urgency. Back in 1998, 2 independent groups of astronomers made a discovery that reshaped our understanding of the universe. They had expected to see the great expansion born in the fire of the Big Bang gradually slowing as gravity tried to draw everything back together. But the universe had a different story to tell. Instead of decelerating, the expansion was accelerating. For almost 14 billion years after the Big Bang, gravity acted as the dominant sculptor, slowing the outward rush and gathering matter into vast clusters of galaxies. The cosmic pace eased steadily. Then, roughly 5 billion years ago, something subtle yet profound shifted. An unknown influence began to overwhelm gravity on the grandest scales. We gave it a name, dark energy, though the term itself reveals how little we truly understand it. We cannot observe it directly, cannot touch it, cannot see it, and yet it governs the universe. It fuels the acceleration that will ultimately dictate the destiny of the cosmos. Our evidence for this invisible force comes from studying ancient stellar explosions called type supernovas. These cosmic detonations erupt with nearly identical brightness, allowing astronomers to treat them as standard candles. By comparing their apparent brightness with their intrinsic luminosity, we measure their distance. By analyzing their redshift, we determine how rapidly they are moving away. When the distances of these supernovas were plotted against their redshifts, astronomers expected a neat linear relationship echoing Hubble's law. Instead, the distant supernovas appeared unexpectedly faint, implying they were far farther away than predicted. Something had pushed them out more rapidly. The expansion of the universe had accelerated, carrying galaxies into deeper cosmic isolation. This accelerating behavior manifests only in the vast low-density voids separating galaxy clusters. Within the clusters themselves, where matter remains densely packed, gravity still holds sway, Dark energy cannot break apart structures already bound together. Its influence emerges only once matter density falls below a critical threshold. This selective behavior has produced a universe of strange contrast. Galaxy clusters sit as gravitationally bound islands amid an ever-widening cosmic sea. The space between these islands grows faster and faster. Any future civilization residing within such a cluster will witness the rest of the universe gradually fade from view as distant clusters slip beyond their cosmic horizon. Current measurements suggest that dark energy constitutes about 68% of the energy content of the universe. Ordinary matter, everything from stars and planets to living beings, makes up less than 5%. Dark matter supplies about 27%. This means that 95% of the universe consists of entities whose nature remains unknown. The origin of dark energy is one of the most profound puzzles in physics. Some theories suggest it may be the energy of empty space itself arising from quantum fluctuations. Others propose that it might stem from dimensions hidden beyond the familiar three of everyday experience. Still others speculate that dark energy evolves with time waxing or waning as the universe matures. Recent findings from the Dark Energy Spectroscopic Instrument hint that dark energy may indeed be changing. If confirmed, such a result would reshape our understanding of cosmology, indicating that the force behind acceleration is not a fixed entity, but something dynamic and potentially linked to new physics. The implications extend far into the deep future. Should dark energy continue to grow stronger, cosmic expansion will accelerate to such an extent that even gravitationally bound systems will be torn apart. First, clusters of galaxies would disperse. Then individual galaxies would dissolve. Ultimately, even atoms may be pulled apart in a scenario known as the Big Rip. Yet the real enigma lies in the fact that dark energy dominates the behavior of the universe while remaining entirely unseen. Imagine taking inventory of the cosmos. Count every star in every galaxy. Add every planet, moon, asteroid, and cloud of gas. Include every black hole, neutron star, and object ever observed. All of this accounts for less than 5% of reality. The remaining 95% comprises two components detected only through their gravitational fingerprints. Dark matter contributes 27%. Dark energy completes the balance at 68%. Neither interacts with light or electromagnetic forces. They elude every instrument we have devised. And while dark matter at least gathers into structures, dark energy displays no such inclination. It is uniformly spread, identical, from one region of space to another. It does not cluster around galaxies. It does not pool in dense regions. Instead, it permeates every cubic inch of space with the same density. This uniformity leads to its most bewildering feature. As space expands, the total amount of dark energy increases in direct proportion to that expansion. Double the volume of the universe and you double the total dark energy. This contradicts our everyday experience of how energy behaves. Stretch a rubber band and the energy stored within changes, but total energy does not magically appear from nothing. Dark energy seems to grow as the cosmos grows. Its density is extremely small, yet its influence is written across the entire universe. Each cubic yard of what we casually call empty space carries a whisper of energy, the dark energy equivalent to roughly 6 hydrogen atoms. On its own it feels negligible, but when spread across the vast sweep of the observable cosmos, it becomes a dominant presence, outweighing the mass energy of every star, every planet, every drifting cloud of interstellar matter by more than an order of magnitude. Several ideas have been put forward to explain this elusive component of the universe. The most prominent suggests that dark energy is simply the energy of the vacuum itself, born of quantum processes that never truly stop. Quantum theory tells us that even the emptiest regions of space simmer with transient particles that appear and vanish in intervals so brief that light could not traverse an atomic nucleus in the time they exist. This restless quantum foam could create a uniform energy density permeating the cosmos. Yet when physicists attempt to calculate its magnitude, the result overshoots reality by a factor of 10, followed by 120 zeros, a mismatch. So staggering, it stands as the most spectacular failure in the history of theoretical physics. Such an error forces an uncomfortable choice. Either quantum mechanics is missing something profound, or dark energy arises from an entirely different source. Some scientists imagine that dark energy might be a consequence of dimensions beyond the familiar three that shape our daily experience with gravity, seeping into these hidden realms over cosmic distances and producing the illusion of acceleration without invoking a mysterious energy field. Others suggest that dark energy may not be fixed at all, that its influence waxes and wanes as the universe evolves. Hints from recent astronomical surveys lend weight to this possibility. Measurements from the Dark Energy Spectroscopic Instrument reveal slight but intriguing variations in how dark energy behaves across cosmic time. Should these variations be confirmed, we would be compelled to explore physics beyond anything currently known. Because dark energy dominates the cosmic ledger, ordinary matter plays only a supporting role in determining the universe's long-term destiny. Stars, galaxies, and every atom that makes up our bodies are minor embellishments in a universe governed by forces we cannot directly sense. Everything familiar to us arises from the scant 5% of reality that is visible and comprehensible. This extraordinary composition urges us to reflect on our place in the grand scheme of things. We are shaped from rare material in a cosmos ruled largely by the unseen and the unexplained. All the galaxies we observe with their billions of stars form only a slender fraction of what truly exists. And yet, despite the progress made by modern cosmology, increasingly precise measurements have exposed a deeper puzzle at the heart of our understanding. Two independent techniques for measuring the expansion of the universe yield conflicting results, shaking the foundations of cosmology. The tension emerged as our instruments sharpened. Astronomers expected their measurements to converge, but instead encountered a stubborn and growing divergence. The two methods disagree by about 9%. It may sound small, but both methods achieve precision at the level of a few percent, meaning the discrepancy cannot be shrugged off as observational noise. Something fundamental eludes us. One method examines the cosmic microwave background, the faint relic light, from a time when the universe was only 380000 years old. Encoded in its delicate temperature variations is a blueprint of the cosmos that allows scientists to infer the present rate of expansion. This approach produces a value near 67 kilometers per second per megaparsec. The other method looks much closer to home, measuring distances to nearby galaxies using pulsating stars known as Cepheid variables. These cosmic beacons brighten and dim in steady rhythms tied directly to their true luminosity. By comparing their intrinsic brightness to how bright they appear, astronomers can gauge distances with extraordinary accuracy. This local approach yields a value around 73 kilometers per second per megaparsec. The 6-unit gap between these results has become a genuine crisis. If the cosmic microwave background value is right, distant galaxies should sit closer than they seem. If the local value is right, then the physics of the early universe must be revised. In either case, a flaw lies deep within our cosmological framework. The team responsible for the local measurements has spent decades refining their methods, probing every potential source of error, and each refinement confirms the higher value of 73. The analysis of the cosmic microwave background carried out by the Planck mission consistently points to a lower expansion rate around 67. Independent teams across the world using entirely different approaches arrive at the same conclusion. Some turn to type Ia supernovae rather than Cepheid variables. Others examine the gentle distortions of gravitational lensing or the faint ripples of surface brightness within distant galaxies. Closer to home measurements repeatedly cluster near 73. In the deep past they settle around 67. This persistent divide hints that somewhere in the long arc of cosmic history, something profound unfolded that our current model fails to capture. Perhaps dark energy evolved in ways we have yet to understand, or maybe unfamiliar particles shaped the expansion during those first formative billions of years. There are theories that suggest space itself may possess properties we have not yet uncovered. And this is not merely an academic puzzle. The Hubble constant underpins our calculations of the universe's age, delineates the distances to galaxies, and influences the very trajectory of cosmic expansion. If we cannot determine this foundational parameter with confidence, then the framework on which modern cosmology rests becomes uncertain. Efforts to untangle this tension have only thickened the mystery. Some argued that nearby measurements must contain hidden biases. Others suspected that assumptions embedded in the cosmic microwave background analysis might be misguided. Yet meticulous examinations have largely dismissed these concerns. Into this debate stepped the James Webb Space Telescope, carrying the expectation that it might finally bring clarity. With its extraordinary precision and sensitivity, it seemed poised to resolve the disagreement. Instead, its observations have deepened the enigma. The most capable observatory ever constructed now reinforces the very results that unsettle our understanding. Many hoped it would expose unnoticed flaws in earlier data. Instead, it has delivered the strongest confirmation yet that our cosmological picture is incomplete. The mismatch in expansion rates is not an illusion. It persists, and it calls for new physics. Webb's infrared gaze cuts through dust that once obscured vital markers, revealing Cepheid variables with remarkable clarity in galaxies as distant as 130 million light-years. These rhythmic beacons serve as cosmic yardsticks, and Webb measures them with exquisite precision. Its results align with Hubble's to within a single percent, confirming that the local expansion rate cannot be explained away through observational errors. What remains is a tension that grows sharper as the data improve. Two of NASA's flagship observatories, operating through entirely independent methods, now converge on the same figure: 73 kilometers per second per megaparsec in our cosmic neighborhood. This outpaces the early universe prediction by about 9%. Webb's findings draw from the most extensive collection of distance indicators ever assembled, examining more than 300 Cepheid variables in nearby galaxies and cross-comparing them with carbon-rich stars and fluctuations in surface brightness. Regardless of technique, the picture remains the same. The local universe expands more rapidly than models rooted in the early cosmos would allow. Such confirmation forces the field to grapple with unsettling possibilities. Either our portrait of the early universe requires fundamental revision, or as yet unknown physics influences the growth of space itself. Either path demands rethinking a model that has elegantly explained observations for decades. Yet within Webb's data lie subtle hints that may point the way forward. The telescope sees delicate variations in the expansion rate depending on the direction one looks. Some regions drift outward slightly faster, suggesting that dark energy may not be perfectly smooth across the cosmos. Though the differences are minute, they challenge the long-held assumption that expansion is entirely uniform. Webb also reaches farther back in time than previous observations, capturing Cepheid variables whose light has been traveling for over 100 million years. This expanded window lets astronomers trace how the expansion rate has evolved, offering new constraints on the elusive behavior of dark energy. Webb's confirmation echoes across the vast architecture of the cosmos. If the universe is indeed expanding more rapidly than we thought, then its age contracts by nearly 1 billion years, reshaping everything from the birth of galaxies to the long arc of stellar evolution and the slow emergence of cosmic structure. Even our estimates of dark energy's density and the universe's long-term destiny shift beneath this new light. One of the scientists guiding these exquisitely precise measurements describes the moment as both a challenge and a remarkable window into the unknown. The mismatch between predictions and observations hints that our understanding of the universe may be incomplete, inviting the possibility of entirely new physics that could transform cosmology. Ideas at the frontier attempt to account for this tension. Some imagine an early form of dark energy that briefly influenced the young cosmos before fading away. Others suggest hidden dimensions that alter the behavior of gravity on the grandest scales, or propose that dark matter and dark energy may interact in ways that evolve with cosmic time. Webb's confirmation also touches the craft of astronomy itself. Every map of distance, every measurement of a supernova's brilliance, every model of the universe's three-dimensional shape depends on the expansion rate. With the Hubble tension unresolved, uncertainty permeates these calculations and spreads outward into countless astronomical investigations. To unravel this puzzle, we may need to look beyond ordinary light, reaching deeper into the foundations of cosmic expansion. The universe's earliest portrait captures the instant when space became transparent and the great deceleration of expansion began. About 380000 years after the Big Bang, the young cosmos flared like a primordial camera flash. For the first time since time itself began, light could move freely. This ancient glow still permeates the universe, carrying with it the story of expansion from an era when the cosmos was less than 1% of its present age. Before this turning point, the universe was so unimaginably hot and dense that electrons could not bind to nuclei. Light ricocheted endlessly off free electrons, shrouding the young cosmos in a fog as opaque as the interior of a star. Nothing could be seen. Even the sharpest eyes would fail to pierce more than a few inches of this radiant haze. Then, as the temperature dropped to about 3000 degrees, electrons merged with protons and helium nuclei to form the first stable atoms. In that moment, the fog dissolved. Astronomers call this cosmic clearing recombination. The entire universe became transparent in an instant. The light released then has been traveling for 13.4 billion years, stretched by expansion from visible wavelengths to the microwaves we now detect. This cosmic microwave background fills every cubic inch of the universe with faint radio light at just under minus 454 degrees Fahrenheit. Its uniformity across the entire sky is astonishing. Temperature variations are smaller than 1 part in 100,000. At first, this sameness posed a profound puzzle. Regions separated by billions of light years share identical temperatures, despite never having had time to exchange information at light speed. Cosmic inflation resolves this mystery. In the first fleeting fraction of a second, space expanded far faster than light could travel. Tiny smooth patches of the early universe were stretched to enormous scales, preserving their uniform temperatures across vast reaches of space. Within this gentle smoothness minute, ripples of warmth and coolness appear. These subtle variations mark the seeds from which the first galaxies would emerge. Slightly warmer regions held a little more matter. Over millions of years, gravity magnified these small differences, sculpting the galaxies and clusters we see today. The cosmic microwave background acts as a blueprint for the universe's grand structure. Through its delicate temperature patterns, cosmologists measure the universe's fundamental properties with extraordinary precision. Space is flat to within 1%. The universe is 13.7 billion years old, give or take 20 million. Dark matter accounts for about 26.8% of cosmic density, while dark energy makes up roughly 68.3%. These measurements also lock in the expansion rate of the universe at the moment of recombination. By weaving together the ancient record of the universe's early expansion with models that trace how that expansion has shifted across cosmic time, we arrive at a prediction that space should grow at about 67 kilometers per second per megaparsec. Yet when we turn our telescopes toward our immediate cosmic surroundings, the measurements disagree by nearly 10%. This discrepancy hinges on our interpretation of the cosmic microwave background, whose delicate patterns encode more than 13 billion years of cosmic evolution. Even the slightest alteration in the universe's expansion history imprints itself on the temperature variations we observe today. Our standard cosmological framework, built on dark matter and dark energy, reproduces these patterns with astonishing precision, and yet it falls short when it comes to the expansion rate unfolding in our own neighborhood. Such a mismatch suggests one of two possibilities. Either our reading of the cosmic microwave background contains subtle elusive errors, or our cosmological model lacks crucial physics that shapes the growth of space itself. Observations from the Planck satellite have already pushed the precision of these measurements to their practical limit, mapping temperature variations to better than 1 part in a million. These exquisitely detailed observations validate the Standard Model's predictions, while simultaneously illuminating the unresolved tension with direct measurements of cosmic expansion nearby. The cosmic microwave background offers our most profound glimpse into the universe's past, yet it cannot penetrate the first 3,800,000 years, when space remained opaque to light. In a fraction of a moment, far briefer than anything we can meaningfully imagine, space erupted outward faster than any physical process we have ever observed. Before atoms existed, before light could roam freely, the universe experienced the most dramatic growth in its history. This event, known as cosmic inflation, concluded in less time than it takes a photon to complete a single vibration. And yet, during that fleeting instant, space swelled by a factor that dwarfs the number of atoms within the observable universe. Envision a region smaller than a subatomic particle containing all the matter and energy that would someday form billions of galaxies. Then picture that tiny seed inflating to the size of a grapefruit in an instant. That represents only the minimum expansion required by inflationary theory. The real expansion could have been incomprehensibly larger. In 1980, the idea of cosmic inflation was introduced to resolve several profound mysteries of the Big Bang. The cosmos appears astonishingly smooth and flat, even though regions now separated by billions of light years were never close enough to share information at light speed. Inflation solves this by taking a minuscule uniform patch of space and stretching it to cosmic scales faster than light could move across it. The field responsible for driving this expansion remains unknown. Physicists refer to it as the inflaton, though its true nature continues to elude us. This enigmatic field imbued space with tremendous energy density, propelling its exponential growth. Eventually, the inflaton decayed, releasing its energy into the hot plasma that filled the young universe. During this extraordinary period, quantum fluctuations were pulled from microscopic scales to sizes large enough to seed every cosmic structure that would ever form. Without inflation, the universe would have remained perfectly smooth, devoid of galaxies, stars, or planets. The mathematics behind this process defy ordinary intuition. Merely 60 E-foldings, each representing a doubling of the universe's size, would inflate space by a factor of 1, followed by 18 zeros. Many models propose hundreds of such doublings, producing expansions that surpass even the number of particles in the observable universe. This vast stretching of space explains why the cosmos appears so remarkably flat. Just as a balloon's surface looks increasingly planar as it inflates, the exponential growth of the universe erased any trace of its initial curvature. Inflation also accounts for the near-perfect uniformity of the cosmic microwave background. Regions now separated by unimaginable distances once emerged from the same tiny domain before inflation tore them apart, faster than light could travel between them. When inflation came to an end, the universe entered a phase known as reheating. When the inflaton field released its energy, it dissolved into a sea of elementary particles, flooding the young cosmos with a blisteringly hot and dense plasma. In that moment, what we think of as the Big Bang truly ignited. This reheating forged every particle of matter and every photon of radiation that now populate the observable universe. Our confidence in this extraordinary idea comes from exquisitely precise measurements of the temperature variations imprinted on the cosmic microwave background. Those delicate ripples trace the fingerprints of quantum fluctuations, stretched across cosmic scales by the universe's exponential ballooning. The remarkable harmony between these predictions and what we actually observe lends powerful support to the inflationary picture. Yet inflation itself remains beyond direct sight for the microwave background, formed almost 400,000 years after inflation had ended, leaving us to reconstruct that primordial era from its afterglow. Even so, there are hints that inflation may have left deeper marks upon space-time. It may have stirred up primordial gravitational waves that still ripple faintly through the cosmos. These waves would inscribe subtle swirling patterns in the polarization of the microwave background patterns that future observatories may one day reveal. And if they do, we will be glimpsing vibrations set in motion at the dawn of everything. But inflation speaks to more than the universe's astonishing uniformity. It reaches toward the underlying architecture of reality itself. The cosmos must take on one of three possible shapes, and only one of them allows space to expand without end. Just as you can bend a sheet of paper into different forms, so too can space-time curve and fold, dictating the destiny of cosmic evolution. A flat universe stretches outward infinitely, utterly straight, with no curvature at all. In such a cosmos, parallel lines never converge or diverge, and every triangle's angles add neatly to 180 degrees. Expansion carries on, eternally slowing, but never halting, as galaxies drift apart across an endless expanse. Imagine an infinite plane where straight lines never meet, and every geometric rule behaves exactly as it does in familiar Euclidean space. This is the three-dimensional analog of the flat geometry we navigate every day. A closed universe, by contrast, bends back upon itself like the surface of a sphere. Here, parallel lines ultimately meet, just as lines of longitude touch at Earth's poles, and triangles boast angles that sum to more than 180 degrees. In such a cosmos, expansion is only temporary. Eventually it reverses, collapsing inward toward a final singularity, a mirror of the Big Bang. Walk across the surface of a vast sphere, and without ever turning, you will eventually return home. It feels infinite as you journey, yet the entire world remains finite. In 3 dimensions, a closed universe curves in exactly this way. The third possibility is an open universe shaped like a cosmic saddle, in which space curves away from itself. Parallel lines drift apart. Triangles fall short of 180 degrees. Here expansion not only continues forever, but accelerates relentlessly. Galaxies race away from each other at ever-increasing speeds until the cosmos grows cold, dark, and profoundly empty. Imagine tracing 2 lines across a saddle-shaped surface and watching them diverge. Negative curvature fuels expansion that no force can slow. Which of these grand architectures describes our universe depends entirely on the amount of matter and energy woven into its fabric. High density bends space into a closed form, low density into an open one, and a very specific critical density produces perfect flatness. This critical density is astonishingly small, roughly equivalent to the mass of 6 protons scattered through every cubic yard of space. Observations reveal that our universe lies uncannily close to this value. Measurements of the microwave background indicate flatness to within about 1%, as though the cosmos were delicately poised between all possible fates. This near-perfect balance baffled cosmologists for years. Why should the cosmic density be tuned so precisely that space appears flat? Inflation elegantly resolves this puzzle. During the universe's earliest instance, space expanded so violently that any hint of curvature was stretched away until it became imperceptible, just as a balloon's surface looks flatter as it grows. But this serene geometric picture is complicated by dark energy. Even in a flat universe, the repulsive influence of dark energy can overpower the deceleration expected from matter alone. Rather than slowing gently, cosmic expansion now accelerates. The universe will continue its growth forever unless dark energy evolves. Should it strengthen, it could overwhelm every binding force in existence. Should it weaken, expansion might slow or conceivably reverse despite the underlying flatness. Recent high-precision measurements remind us that identifying the universe's true geometry requires confronting this extraordinary balance between matter, energy, and expansion. The cosmos contains just enough mass to sit exactly on the threshold between eternal growth and inevitable collapse, 6 protons worth in each cubic yard of space. Slightly more mass and gravity would win, dragging everything back toward a final crunch. Slightly less, and expansion would accelerate without end, leaving behind an empty frozen void. Yet our universe rests within a mere 1% of this dividing line. This exquisite fine-tuning raises a profound question that has echoed through cosmology for decades. Why should our universe carry almost exactly the amount of matter required to balance on the edge of eternity? It could have been unimaginably denser or vanishingly sparse, and yet it hovers with delicate precision at the boundary between collapse and endless expansion. The notion of critical density arises from a delicate interplay written into the fabric of the cosmos itself. On one side lies gravity forever tugging at the universe, gently urging the expansion born in the Big Bang to slow. On the other is the primordial outward rush, the momentum of creation, carrying galaxies apart across unimaginable distances. Critical density is the exquisite point of balance between these two vast influences. It is much like launching a ball from Earth. Give it too little speed, and our planet's gravity draws it home again. But hurl it upward with sufficient velocity, around 25,000 miles an hour, and it escapes Earth's grip entirely. That threshold mirrors the way the universe behaves on the grandest scale, with the critical density acting as a cosmic escape criterion that decides whether the universe will expand without end or eventually fall back in upon itself. This balance becomes stranger still when we trace it back through cosmic history. In the young universe, matter crowded together so densely that its value far exceeded the critical threshold. As space swelled, matter thinned out. At the same time, the very value of the critical density fell as the cosmic expansion eased. The two changed in concert, tracking one another with uncanny precision over billions of years as though choreographed. Yet, the chance of such synchrony unfolding randomly is negligible. Had the early universe begun with a density even a billionth above or below the critical value, it would have collapsed in moments or blown apart so fiercely that no galaxies, no stars, no planets could ever have taken shape. Inflation offers a compelling possibility for how such fine-tuning emerged. In that first tiny sliver of a second space, expanded exponentially, ironing out any irregularities and driving the density toward the critical value, regardless of where it began. But the story becomes more intricate with the introduction of dark energy. While matter and radiation thin as the universe expands, dark energy does not. It remains steadfast, and with time it becomes the dominant contributor to the cosmic budget, overtaking both matter and the carefully tuned balance of densities. Today it makes up roughly 68% of the universe, leaving matter with about 32%. The result is that the total density actually exceeds the critical value, yet the universe accelerates outward because dark energy's repulsive influence outweighs matter's gravitational pull. This puzzle threads into deeper questions about why the laws of physics seem so exquisitely arranged to allow complexity to exist at all. Some imagine a landscape of many universes, each with different properties, and we find ourselves in one compatible with life, simply because we could not have emerged in the others. Others suspect that undiscovered principles, perhaps rooted in quantum gravity or hidden dimensions, naturally drive the cosmos toward this delicate equilibrium. And yet, recent speculations push the boundaries even further. One provocative idea suggests that the accelerating expansion has nothing to do with mysterious energy fields. Instead, the universe might be growing because it continually absorbs minuscule parallel realms, tiny newborn universes flickering into existence from quantum fluctuations. In this vision, our universe swells, not due to an invisible force permeating space, but because each microscopic collision adds a little more space to our own. Imagine soap bubbles gathering in a warm bath, the smaller ones gliding across the surface until they fold into the larger spheres, allowing them to swell and reshape. In this vision of the cosmos, our universe becomes the grandest bubble in a vast foam of realities. Tiny embryonic universes slip into ours like quantum bubbles, adding their volume to the fabric of space as it stretches outward. They remain forever hidden from us, residing in dimensions beyond the 3 coordinates we can navigate, touching our world only through the faint pull of gravity. To us, their merging reveals itself as the silent expansion of the cosmos, powered by what we have long called dark energy. Yet the mathematics whispers something intriguing. When the expected rate of expansion caused by these mergers was calculated, it aligned with observations more closely than the traditional models that rely on mysterious ingredients composing most of the cosmos. In this framework, the acceleration does not demand an unseen reservoir of unknown substances. Instead, it springs from the quantum nature of reality itself, where empty space is never truly empty, but flickers with virtual particles emerging and vanishing in unimaginably brief instants. Under extraordinary conditions, these quantum tremors may ignite entire pocket universes. They begin impossibly small, far beneath the scale of protons, and yet some expand with astonishing speed. Most of these newborn realms remain microscopic, folding themselves into our universe almost at once. Others may grow, cultivating their own physical laws, before ultimately merging back into our reality. This process does not unfold rarely or in isolated corners. It is woven into the entire tapestry of space and time. And so the constant absorption of these baby universes may illuminate mysteries that have long puzzled cosmologists. Perhaps this is why the universe appears so remarkably flat, even though matter should bend its geometry. The steady infusion of new space could wash away curvature, leaving the cosmos level on the largest scales. It may even offer an answer to the cosmic coincidence problem, the question of why the universe possesses just the right balance of properties to allow stars and galaxies to flourish. If countless infant universes with varied traits are continually merging with ours, then over vast periods the most harmonious combinations would naturally become dominant, selected by the unfolding physics of the cosmos. Yet this remains a bold and deeply speculative idea. There is no direct evidence for parallel realities, let alone their ability to merge with our own. It demands extra dimensions and unfamiliar forms of physics that have yet to leave any measurable trace. Most scientists remain cautious, aware that such conjectures drift far from established cosmology. Testing the idea is profoundly difficult. These baby universes reveal themselves only through gravity, making them effectively invisible to our current tools. Future gravitational wave observatories might in principle capture the faint ripples generated by the merging of universes, though separating such signals from the background of the cosmos would be an immense challenge. Still, the consequences are extraordinary. If these mergers occur endlessly, then reality is far more fluid and interconnected than we have ever imagined. Our universe would be but one swelling bubble in a limitless foam growing through a gentle form of cosmic consumption. Critics argue that this merely replaces one enigma with another, exchanging dark energy for unseen universes with precisely the right characteristics. The equations may be elegant, but the evidence remains elusive. Yet the idea gestures toward an even more profound picture of existence. Realities may influence each other across dimensions we cannot map, driving the expansion we observe. And beyond these collisions lies an even deeper possibility. Our universe may sit within an enormous multiverse, a realm where countless parallel worlds shape one another through mechanisms that lie beyond everyday physics. Cosmic inflation once offered the first glimpse of such a structure, revealing that while expansion slowed in our region nearly 14 billion years ago, it likely continues eternally in countless others, spawning an endless mosaic of pocket universes. Each is a self-contained reality with its own laws of nature. They drift within a higher dimensional space, as though our universe were a 3-dimensional sheet suspended in a 4-dimensional sea. Other sheets might hover close by brushing against us, or subtly exchanging energy across boundaries we cannot sense. Some proposals even suggest that what we call dark energy arises from these interactions. If nearby universes hold different reservoirs of matter and energy, their gravitational influence could seep between dimensions, manifesting in our cosmos as accelerating expansion. The mysterious force that shapes the fate of the universe may in the end be the echo of unseen worlds beyond our own. String theory, in its ambition to weave all the forces of nature into a single coherent tapestry, leads us quite naturally to the idea that reality extends far beyond the dimensions we inhabit. In such visions of the cosmos, the particles and forces that shape our everyday world reside on a three-dimensional surface, while gravity alone is free to wander through a grander, multi-dimensional arena. In that freedom lies the tantalizing suggestion that gravity might whisper between parallel worlds, even when every other form of communication is forever sealed. When we follow the mathematics into these high-dimensional landscapes, we encounter possibilities that feel almost surreal. Some universes might experience gravity far more intensely than ours, while others drift in a gentle gravitational haze. Entirely new families of particles or unfamiliar forces could arise in realms where the physical rules diverge from those of our own cosmic home. The interplay between such diverse realities could generate exotic behavior on the largest scales, shaping the evolution of space in ways that resemble the mysterious push we call dark energy. Eternal inflation imagines a cosmos in perpetual creation, where quantum fluctuations in a higher dimensional medium continually give birth to new universes. Ours expands, perhaps subtly perturbed, by the emergence of neighboring worlds. Each fresh universe alters the geometry of the wider multiverse, driving an unending acceleration that ripples through this vast cosmic archipelago. The anthropic principle enters here with profound implications. If there truly exist countless universes, each with its own rate of expansion, then we inevitably find ourselves in one that has the delicate balance required for stars, galaxies, and the long cosmic story that leads to consciousness. Universes that race ahead too quickly or collapse too sluggishly never form the structures needed for life. So observers like us can only appear in a universe where expansion unfolds at just the right pace. Yet despite these compelling ideas, the multiverse confronts us with a profound challenge. Parallel universes by their very nature lie beyond our direct reach. At best, we infer their presence from the faintest clues they might imprint upon our own cosmic environment. This makes such theories extraordinarily difficult to examine through traditional scientific inquiry. Some argue that if a theory cannot be falsified, it slips from the realm of empirical science into something more philosophical, more speculative. Mathematical beauty alone is not enough. Without measurable evidence, the multiverse remains a hypothesis waiting for the cosmos to reveal its secrets. There are hints to search for. Some have suggested that subtle patterns in the cosmic microwave background might betray ancient collisions between our universe and others. Such interdimensional encounters, if they occurred, could leave faint scars upon the oldest light in the sky. Future observatories, with their exquisite sensitivity, may one day uncover these elusive fingerprints. And if the multiverse truly shapes cosmic expansion, then our universe becomes a single bubble floating within an immense froth of realities. Its expansion is a local event set within a structure vastly grander than we can easily imagine. To explore ideas so bold, we must understand the mathematics that describes how space itself evolves. The equations reveal a universe whose fabric stretches effortlessly, increasing the distances between galaxies without requiring them to move through space at all. In 1922, Alexander Friedmann derived these equations from Einstein's general relativity, showing that the universe must be dynamic. Expansion or contraction is inevitable. The notion of a static cosmos was mathematically untenable, even though the observation came later. Friedmann's equations describe how the scale factor changes with time. One can imagine it as a cosmic ruler that lengthens as space grows. When that ruler doubles, distances between galaxies double too. A galaxy 1,000,000 light years away becomes 2,000,000 light years distant, simply because the cosmic ruler has stretched. The rate of this expansion depends on the energy content of the universe. Matter and radiation tug inward, slowing expansion as they dilute over time. Dark energy, on the other hand, exerts a kind of gravitational repulsion that becomes ever more influential as matter thins out. Different eras of cosmic history are shaped by whichever component dominates. Radiation ruled the early universe, followed by matter, and finally dark energy, which began accelerating cosmic expansion roughly 5 billion years ago. The metric tensor encodes the geometry of space-time itself. In an expanding cosmos, the spatial part of that geometry grows while time flows steadily onward. Galaxies do not rush through space. Instead, the very coordinate system that defines space swells around them. Robertson and Walker later broadened these ideas to describe universes that are smooth and uniform on the largest scales, providing a framework flexible enough to encompass many possible cosmic geometries. The cosmological principle lets us take the intricate geometry of space-time and distill it into a single evolving quantity, a scale factor that changes only with cosmic time. The Hubble parameter then becomes a measure of how swiftly that scale factor grows at any moment. It is the expansion rate per unit distance, the simple linear relation that Hubble uncovered in the sky. As the cosmos ages, this parameter falls in universes ruled by matter, yet in eras dominated by dark energy, it hovers close to a constant value. Redshift flows naturally from this picture of metric expansion. As space itself stretches the light crossing, it is stretched by precisely the same amount. If the universe doubles in size during a photon's journey from some remote galaxy, its wavelength doubles too, and the light arrives tinged with a redshift of 2. This redshift is not a Doppler effect arising from motion through space. It is born from space changing as light travels. To estimate the universe's age, we trace the Friedmann equations backwards to the moment when the scale factor contracts to 0. That calculation incorporates the shifting expansion rate over the entire cosmic timeline. With the observed amounts of matter, radiation, and dark energy, the clock points to roughly 13.8 billion years. Co-moving coordinates offer a graceful language for locating objects in an expanding universe. In these coordinates, galaxies carried only by expansion remain at fixed addresses, even though the space between them grows. This approach cleanly separates true motion from the global swelling of space. The critical density appears when we set the Friedmann equations to 0, capturing the delicate balance between gravity's slowing influence and the outward rush required for eternal expansion that asymptotically grinds toward stillness. That threshold density depends on the expansion rate of the present epoch and shifts as the universe evolves. Dark energy enters through its equation of state, linking its density to pressure. Ordinary matter exerts no pressure. Radiation exerts a positive pressure equal to 1/3 of its density, but dark energy carries a negative pressure equal in magnitude to its density, generating the repulsive gravity that accelerates cosmic expansion. The stark simplicity of metric expansion sits uneasily beside our intuition. The mathematics describe a realm where distances grow without objects moving, where the fabric of space manufactures more of itself, where geometry transforms with time. Such ideas challenge everyday experience, yet match cosmic observations with striking accuracy. They even point toward a deeper strangeness. Expansion has no central point and no frontier. It proceeds everywhere at once, giving each vantage point the illusion of being at the center, while none truly is. Stand anywhere in this vast universe and gaze outward. Galaxies withdraw from you in every direction, as though you occupy the fulcrum of expansion. Travel to another galaxy, and you will witness the same pattern. From that new position, the cosmos again appears to race away on all sides. This mirage arises from the uniform expansion of space. Because every region stretches at the same rate, each observer sees precisely the same recession pattern. There is no privileged location. Nowhere can claim to be the true hub of expansion. When the scale factor increases, every distance grows by the same proportion. Double the scale factor, and every separation between galaxies doubles. Such uniformity cannot possess a center because it acts identically everywhere. Imagine an endless grid of squares, each representing a galaxy. Stretch the grid so that every square doubles in size. From the viewpoint of any single square, all others retreat, especially those that began farther away. No square can declare itself the center of that transformation. Or picture a balloon with dots on its surface. As the balloon inflates, each dot drifts from all the others. From the perspective of any dot, it remains still while the rest recede. The expansion belongs to the surface itself, which has no center on that two-dimensional sheet. Our three-dimensional universe behaves in precisely this way. Space expands evenly in all directions from every location. Each observer feels at the center only because expansion is universal, not focal. Every point participates equally, and because there is no center, there can be no edge. If there were a central point, there would need to be boundaries marking where expansion begins or ends. Instead, on the largest scales, the cosmos presents the same face in every direction. The cosmological principle suggests a universe that stretches without limit, or one that folds back on itself so smoothly that no boundary could ever be found. Even if its total size is finite, there would be no cliff edge where space simply stops. Much like wandering endlessly across Earth's surface, you could journey through such a cosmos without ever encountering a frontier. The surface of a sphere offers a familiar analogy. It encloses a limited area, yet nowhere does it present an edge. In the same way, a finite universe could possess a limited volume while remaining entirely edgeless. The Big Bang was not an eruption from a single spot, but a moment in which all of space shrank to zero size and then began to grow. Every location took part equally in that vast unfolding. There was no bursting shell of debris flying through emptiness, because there was no external void waiting to receive an explosion. Cosmic expansion unfolds through a different logic. Space itself swells and carries galaxies with it. The universe does not expand into anything beyond because there is no outside. Its expansion has no privileged center, and this is why the ancient light of the cosmic microwave background reaches us uniformly from every direction. That radiation comes from a time about 380,000 years after the Big Bang, when the universe first became transparent. Every region witnessed that transition, so we see its afterglow in all parts of the sky. If expansion had begun from a single point in space, the microwave background would gather towards some favored direction. Instead, its smooth distribution testifies to a cosmos expanding everywhere all at once. This insight carries us toward the future. With no center and no boundary, the acceleration driven by dark energy acts on the entire cosmic stage, simultaneously stretching space and sending galaxies racing away from one another at ever-increasing speeds. Over immense spans of time, this relentless acceleration leads to a bleak prediction. The energy of the universe will be dispersed across an ever-growing expanse. The warmth and brilliance of stars will fade. In roughly 100 trillion years, the final star will exhaust its fuel, plunging the universe into a darkness so deep that our present age will seem like the flash of a match. Yet that darkness marks only the beginning of an almost incomprehensible journey toward complete emptiness. As expansion continues, the universe cools and thins. Eventually, nothing will remain capable of producing anything new. Bound by the second law of thermodynamics, the universe obeys a simple rule: entropy must rise. Heat flows from hot to cold until all temperatures even out, and in a perpetually expanding universe, that leveling continues until energy is spread so widely that nothing further can be done with it. When the cosmos is about 1,000 times older than it is today, gravity will no longer be able to gather gas into new stars. The stars that already shine will burn through their fuel and die, and no fresh lights will take their place. The stellar era will end. Those extinguished stars leave remnants behind. White dwarfs, neutron stars, and black holes will drift in a cosmos, growing ever more desolate as expansion stretches space between them. Over hundreds of trillions of years, white dwarfs will cool into dark, crystalline husks. Neutron stars cooling even more slowly will take trillions of times the universe's current age to approach absolute zero. These remnants will be the last warm islands in a deepening cosmic winter. Black holes endure still longer, yet their fate is sealed as well. Hawking revealed that black holes emit radiation and slowly lose mass over staggering epochs. A black hole as massive as the Sun would need a number of years so large that it could be written as a 1 followed by 67 zeros to fully evaporate. The titans of the cosmos, containing billions of solar masses, will persist for durations so immense that expressing them would require more digits than atoms in the observable universe. And yet even these giants will eventually evaporate, dissolving into a faint drizzle of particles. When the final black hole fades, only electrons, positrons, neutrinos, and photons will remain scattered like dust across an immeasurable void. As the universe stretches ever outward, the particles within it drift apart until their encounters become vanishingly rare. The glow of the cosmic microwave background thins into almost nothing, its warmth diluted to energies so faint they hover just above absolute zero. Even the proton, that sturdy cornerstone of atomic structure, may not endure indefinitely. Some ideas in modern physics suggest that protons themselves might one day succumb to decay over intervals so immense they eclipse the lifetime of evaporating black holes. Should that be the case, matter as we know it will gradually unravel. What remains is a gossamer mist of electrons, neutrinos, and other lightweight particles drifting through space with virtually no interaction at all. It is the universe sliding toward its final featureless state, a place where energy spreads so evenly that temperature itself loses all meaning. Without temperature differences, nothing can turn, nothing can burn, and no process can unfold. It is a vision of a cosmos settling into perfect thermodynamic stillness, provided that dark energy holds steady across time. But if dark energy strengthens its grip, the ending becomes far more dramatic. The expansion would accelerate until it overwhelms every binding force in nature. Galaxies would be pulled apart, stars unstitched, planets shattered, and even atoms ripped open. Instead of drifting into cold silence, the universe would end in a storm of cosmic disintegration. And yet, if dark energy were to fade or reverse its influence, the great expansion could slow, stop, and then collapse back inward, gathering all matter and energy into a final implosion, setting the stage for another cosmic beginning. Observations today point toward a gentler, colder destiny. Dark energy appears nearly constant, favoring the slow slide into darkness over the cataclysmic alternatives. A future where space expands so completely that events themselves become rare then impossible. But even now, beyond the boundary of what we can observe, lie realms pushed beyond our reach by expansion. These regions of reality already lost to us may harbour unimaginable wonders or terrors. 46 billion light-years away in every direction stands the frontier of all we can ever know. Beyond that horizon, space recedes, faster than light can return information to us. Entire cosmic landscapes slip away forever. They may host impossible civilizations, unfamiliar physics, or even mirror versions of ourselves living out parallel histories. Our observable universe is merely a single bubble within a possibly infinite expanse. And if space truly extends without limit, then everything permitted by the laws of physics must happen somewhere, not once, but endlessly. There would be infinite suns, infinite earths, infinite versions of every life that has ever been lived. The underlying logic is simple. A finite number of possible arrangements repeated across an infinite canvas ensures repetition. Your exact pattern of atoms, your thoughts, your memories, your present moment would recur countless times across unreachable cosmic distances. Even now, the cosmic horizon pushes outward at the speed of light, uncovering new stretches of space. Yet the acceleration driven by dark energy outruns that expansion of our field of view. More galaxies slip away beyond sight than arise within it. The visible universe shrinks in content even as it expands in scale. For future observers, the sky will grow emptier. One by one, galaxies will vanish beyond the horizon until only the small collection, gravitationally bound to our own, remains. Those distant descendants will gaze into a cosmos stripped of its vastness, never knowing the multitude that once filled the night. Beyond their horizon and ours, the laws of physics themselves may shift from one domain to the next. If inflation carved the cosmos into separate regions with differing properties, then some realms may contain stronger gravity, some weaker, some no dark energy at all. Space could unfold in more dimensions or fewer. Particles and forces could play by rules utterly foreign to us. An infinite portfolio of cosmic experiments sealed away by the expansion of space. Civilizations could flourish there, unimaginably advanced, with technologies that reshape space-time or communicate across boundaries we consider absolute. They might have solved mysteries we have only begun to articulate. Or those realms could host extremes far beyond anything we have encountered. Black holes so vast they swallow galaxies. Waves of vacuum decay, erasing reality at light speed. Phenomena so alien they unravel the very structure of physical law. The idea of a multiverse invites us to imagine that beyond the limits of our observable cosmos lie not simply farther reaches of our own celestial landscape, but entire realms with their own space and time. These hidden worlds would drift through a grander dimensional arena, one that stretches beyond the three-dimensional space we move through each day. Each cosmos would unfold according to its own laws, its own rhythm of expansion, untouched by the history that shaped ours. Some of these parallel domains might echo our own so closely that they feel like reflections differing only in subtle inversions. Others could be so wildly unfamiliar that our universe, with all its wonders, appears almost ordinary beside them. Taken together, this vast family of possible universes, the multiverse could represent an infinite tapestry of cosmic expression. Yet if such regions exist forever beyond our reach, they force us to confront uncomfortable questions about the limits of scientific inquiry. If no instrument we build and no observation we make can ever reveal what lies past our visible horizon, can we still claim to grasp the workings of the cosmos as a whole? Science is rooted in evidence, but the accelerating expansion of the universe enforces a horizon beyond which evidence will never arrive. That horizon forms the boundary of what we can know, even as it hints at deeper mysteries. It draws our attention to the astonishing fact that space itself is speeding up its expansion. The agent behind this acceleration, dark energy, strengthens its influence as the universe ages, guiding cosmic evolution toward a future we cannot yet fully imagine. Intuition would suggest that expansion should slow. All matter exerts gravity, a gentle but persistent pull that tries to gather everything together. This cosmic breaking should have gradually defeated the initial blast of the Big Bang. Instead, observations show the opposite. Expansion is accelerating, driven by dark energy overwhelming gravity on the largest scales. This shift began roughly 5 billion years ago, when the universe was about half its current age. Before that turning point, expansion behaved as expected, slowing steadily because matter was dense and gravity strong. As the universe grew, matter thinned out, its gravitational grip weakened, and dark energy emerged as the dominant driver of cosmic evolution. Today, dark energy appears to make up around 68% of the universe's total energy. This share will continue to rise as matter becomes increasingly dilute. In the far future, dark energy will shape the cosmos more completely than ever before. Early results from a spectroscopic survey even hint that dark energy may not remain constant, but could evolve with time, a possibility that would transform our understanding of cosmic destiny. If dark energy strengthens as the universe ages, acceleration could build to such extremes that it tears apart every structure bound by gravity. Galaxy clusters would be the first to unravel. Entire galaxies would follow as their stars drift into the expanding void. Estimates suggest clusters would come apart in about 20 billion years, with the Milky Way dissolving shortly thereafter. Our solar system would disintegrate minutes before Earth itself is ripped apart as dark energy overpowers the forces binding atoms. But if dark energy weakens, the universe might slow its expansion, halt, and eventually contract. Such a cosmic reversal could culminate in a big crunch, gathering all matter and energy into a final point, possibly paving the way for another eruption of expansion. Some models propose that dark energy may oscillate, driving alternating eras of acceleration and deceleration. In this view, our current epoch is one moment in an eternal sequence of expansions and contractions, a universe perpetually reborn. As acceleration continues, it reshapes the very geometry of space and time, pushing the cosmos toward an exponentially expanding form reminiscent of the inflationary burst that occurred in its earliest moments. In the deep future, the expansion of the cosmos may begin to echo those extraordinary moments immediately after the Big Bang, when space itself stretched with almost unimaginable speed. As this acceleration gathers pace, it will slowly draw a curtain across the sky, carrying every galaxy beyond our cosmic horizon until only the small island of our local group remains. All else will slip into the darkness, unreachable and unseen, leaving future observers surrounded by a vast ocean of empty space that grows ever more dilute and distant. In such a universe, astronomers of the far future will have no hint that their night sky was once crowded with billions of galaxies. Even the faint glow of the cosmic microwave background, that whisper from the universe's earliest moments, will drift to ever longer wavelengths. Its energy will fade from microwave to radio, then to the far reaches of the infrared, and eventually to wavelengths so stretched that they become impossible to detect. The last relic of the universe's childhood will quietly disappear as the expansion thins its energy below any possible threshold of observation. More enigmatic still is the way this accelerating expansion seems woven into the quantum fabric of reality. Dark energy may arise from the quantum properties of the vacuum itself, hinting that empty space is not a void, but a profound and fundamental aspect of the universe. And yet it is only one part of the unseen machinery shaping cosmic history, for there is another shadowy component whose gravity sculpts the very structure of space as it expands. Dark matter, far more abundant than the atoms that build stars and planets, acts as the cosmic framework upon which galaxies take form. While dark energy urges expansion to accelerate, dark matter dictates how that expansion influences the growth of structure. Completely invisible and interacting only through gravity, this elusive substance comprises over a quarter of the universe. It cannot be touched, trapped, or illuminated, yet its presence is unmistakable in the way it bends space and alters the patterns of expansion. Where dark matter gathers its gravity slightly, slows the stretching of space, allowing ordinary matter to accumulate. Over cosmic time, these gentle variations guide gas into dense knots where galaxies ignite. Without this invisible scaffolding, the universe would have expanded too smoothly, preventing any grand structures from ever emerging. The cosmic microwave background still bears the faint imprint of these primordial concentrations, tiny ripples in temperature that reveal where dark matter lay when the universe was a mere 3,800,000 years old. Across billions of years, these ancient seed patterns grew as dark matter pulled atoms into the same regions, weaving the vast filaments and clusters that form the cosmic web we map today. Yet the very nature of dark matter remains unknown. It cannot be made of familiar atomic particles, nor can it be composed of photons or neutrinos which refuse to clump together under gravity. It must consist of something new, something hinted at by theories that extend beyond the standard model of particle physics. Perhaps it is made of weakly interacting massive particles, WIMPs forged in the early universe, but so reticent in their interactions that they evade every detector except gravity itself. Or perhaps the answer lies in primordial black holes formed in the universe's infancy, or in sterile neutrinos that barely acknowledge the existence of anything else, or in axion particles that arise from the subtle trembling of quantum fields. Each idea paints a slightly different picture of how dark matter influences the expansion of space. What is clear is that dark matter forms the great underlying architecture of the cosmos. It stretches across unimaginable distances in giant filaments, connecting dense hubs where galaxy clusters assemble. This hidden structure dictates the possible paths of cosmic evolution. Where dark matter pulls, the expansion slows just enough for gravity to draw gas together so that stars and galaxies may be born. In the vast low-density regions, the expansion races ahead, leaving behind immense voids almost entirely devoid of matter. Even on the scale of individual galaxies, dark matter plays a crucial role. Its gravitational pull forms deep wells that bind galaxies together, preventing the accelerating universe from tearing them apart. Without the invisible binding of dark matter, galaxies would simply drift apart as the expansion of space overwhelms the modest pull of their ordinary matter. When we run the universe forward inside our computers, we see dark matter weaving intricate forms on every scale, from the halos that cradle individual galaxies to the great filaments stretching across cosmic space. These structures grow as gravity tirelessly gathers matter into ever richer patterns. Yet while expansion pushes structures away from one another, dark matter draws them together, creating the grand hierarchy we observe. It is a quiet contest between dark matter and dark energy, each shaping the universe in its own way. Dark matter seeks to build and deepen cosmic architecture, while dark energy accelerates the expansion and works against the formation of anything new. As the ages roll on and dark energy continues to rise in influence, it will bring structure formation to a permanent end. One distant day, gravity will simply no longer have the strength to pull matter together. The dark matter framework that once guided cosmic growth will fade into irrelevance as the universe enters an era of runaway expansion. For now, we trace the presence of dark matter by watching how it bends the light of galaxies far beyond our own. Gravitational lensing reveals its role in shaping expansion throughout cosmic time, reaffirming the essential part dark matter has played in building the universe. And still, it remains just one ingredient in a cosmic inventory, extending from the smallest imaginable scales to distances approaching infinity. From quantum fluctuations far smaller than atoms to the sprawling structures that span billions of light years, expansion ties together every level of reality. It operates across a range of sizes beyond ordinary intuition. In the quantum realm, fluctuations summon fleeting particles that appear and vanish in timescales so short they almost defy language. At the opposite extreme, expansion carries clusters of galaxies across unimaginable distances over billions of years. The Planck length marks the smallest meaningful distance in physics, a scale so tiny that below it, the very idea of space loses its meaning. And yet in the earliest instance, inflation stretched quantum ripples at the Planck scale until they became the density variations that later shaped galaxies. In a universe where atomic nuclei sit about 100,000 times above the Planck length, and atoms extend a further 100,000 times beyond, that cosmic expansion leaves these tiny realms untouched. The electromagnetic and nuclear forces that bind matter together utterly dwarf the whisper of gravity responsible for expansion. Even the forces that hold your body intact exceed cosmic expansion by trillions upon trillions. Solar systems measure distances vastly greater than atoms, yet gravity keeps dominion. The sun's pull holds Earth securely in orbit despite the universe expanding beyond its reach. Only in the immense voids between stars does expansion gain ground where gravity declines into weakness. Our galaxy stretches roughly 100,000 light years from side to side, gathering hundreds of billions of stars within its gravitational embrace. It stands as a bound island in an ever-growing sea of space. While the universe expands, the Milky Way retains its shape because its internal gravity far outweighs the gentle push of expansion. Clusters of galaxies reaching spans of 10 million light-years and containing hundreds of galaxies form the largest structures still held together by gravity. Beyond them, expansion triumphs, drawing clusters apart over cosmic time. And through it all, the cosmic web stretches across hundreds of millions of light-years, its filaments of dark matter and ordinary matter linking these vast islands into the grand architecture of the universe. This vast filamentary web, stretching across unimaginable distances, stands as the largest coherent structure we can trace in the cosmos. It emerged as the early universe swelled outward elongating the tiniest ripples in its primordial density, while gravity slowly sculpted them into the intricate patterns we see today. Expansion shapes reality differently, depending on the scale at which we view it. In the quantum domain, it may summon fleeting particles from the vacuum itself as quantum fields respond to the curvature of space-time. At the scale of atoms, expansion is powerless, utterly overshadowed by the forces binding matter together. Across galaxies, it becomes a faint but persistent influence, guiding their long-term evolution. And on the grandest scales, it dictates the geometry of the universe and ultimately determines its fate. The observable cosmos, roughly 93 billion light-years from one side to the other, defines the greatest region we can ever investigate. Within this sphere lie around 2 trillion galaxies each, an island of billions of stars. And yet this immense domain may amount to an infinitesimal sliver of a universe that extends without bound far beyond the reach of our horizon. If space is truly infinite, then cosmic expansion unfolds on scales that outstrip even our imagination. In such an endless expanse, matter and energy repeat without limits, all carried along by the same expansion that shapes our own galactic neighborhood. The physical laws we measure here apply equally to realms forever beyond our sight. Across this hierarchy of scales, expansion binds the entire structure of reality into a single unfolding story. The earliest moments of the cosmos were marked by quantum tremors, tiny fluctuations that served as the seeds of everything that would follow. Over billions of years, they swelled into galaxies and clusters as gravity and expansion danced together. Today, dark energy governs the universe's largest reaches, urging space outward toward futures we cannot yet foresee. The time scales involved are as staggering as the distances. Quantum fluctuations flicker in intervals so brief that light cannot traverse a proton in their duration. The expansion we witness began nearly 14 billion years ago and will continue for epochs so vast that we struggle even to symbolize them. The ultimate sweep of this expansion might lie outside our universe altogether. If ideas of a multiverse are borne out, then our universe becomes one bubble among countless others, each with its own expanding space-time, each embedded in a higher dimensional arena. This would create a limitless hierarchy of expanding worlds, nested within expanding worlds. And across all these realms, from the quantum foam to a potentially infinite collection of universes, expansion forces us to confront a deeper question about our own existence. What does it mean to live in a universe that grows into nothing while carrying everything we know toward an unknowable future? We often ask what the universe is expanding into, and the answer reveals something astonishing. It expands into nothing because it is all there is. Space brings more space into being, as though reality continually conjures the stage upon which its story unfolds. Every atom in your body, every star scattered across the night, every galaxy drifting through the cosmic web is swept along by this expansion, and yet the matter that makes you is rare. The atoms composing your world form scarcely 5% of what exists. The rest is dark matter and dark energy, unseen and deeply mysterious. You are a fleeting configuration of ordinary particles in a universe ruled largely by invisible forces. Your very presence relies on expansion proceeding at precisely the right pace. Had it been faster, galaxies and stars would never have formed. Had it been slower, the cosmos might have collapsed before life ever arose. The expansion rate occupies a delicately balanced middle ground that permitted chemistry, stars, planets, and eventually conscious beings to emerge. Each breath you draw occurs within expanding space-time. The space between your atoms increases by an infinitesimal amount as the universe grows, though the forces holding you together easily resist this stretching. You remain whole while journeying on the vast current of cosmic expansion toward destinations no mind can yet grasp. The light reaching you this evening set out billions of years ago when the universe was smaller and younger. It has been stretched by the growth of space, shifting its colors and carrying with it a record of ancient cosmic history. When you look up, you witness the past while standing firmly in the present of an ever-expanding universe. Your location sits within a galaxy that expands, within a cluster that lies within a universe that may itself be part of a far greater expanding reality hidden from view. This layered architecture of expansion places you quite naturally at the center of the small sphere you can observe, even as it renders you almost vanishingly small within the vastness that may stretch on without limit. The unfolding that began around 13.8 billion years ago will continue for durations so immense that the universe's current age will one day appear no more than the blink of an eye. Long after the sun fades and our galaxy dissolves into the darkness, the accelerating expansion will sweep the scattered remnants of all we have ever known into distances far beyond today's cosmic horizon. The atoms that once assembled your thoughts will drift silently through a frigid universe, edging ever closer to absolute zero, and yet within that stark vision there is a peculiar sense of solace. You are alive during a privileged chapter of cosmic time, when stars still burn fiercely, and galaxies trace graceful arcs across space-time. You take part in this unfolding story at the rare moment when complexity can arise and hold its form, however briefly. Your existence is a fleeting triumph of structure over the relentless march toward ever greater entropy. But the deeper puzzle remains. We can describe space as expanding, pulling galaxies apart at an accelerating pace under the influence of a mysterious dark energy. We can trace this expansion back to the Big Bang and project it forward to a frozen end, or perhaps a cosmic rupture. We know the equations that capture its behavior and the measurements that verify them. Yet the true meaning of expansion in relation to existence itself eludes us. Perhaps the key is not to imagine what the universe expands into, but to recognize that you expand with it. Each moment of your life plays out upon the ever-stretching fabric of space. You think and imagine and create significance while the cosmos unfurls around you. Your conscious mind becomes one way the universe experiences its own growth. And so the central question extends beyond physics into philosophy. If the universe expands into nothing while holding everything within itself, what might that reveal about the nature of being, of awareness, of meaning? You inhabit a cosmos that grows steadily stranger the more we grasp it, yet one that follows impeccable mathematical order, transient in its details, yet woven into an unending story. In the end, this grand expansion links you to the most profound riddles of reality, while quietly reminding you that to exist at all is already one of the universe's most extraordinary achievements.